Have you ever stopped to think how one single element, carbon, is the master architect behind pretty much everything? From simple plastics to the incredibly complex machinery of life itself? Well, today we're going to decode its secret blueprints and see just how it builds the world around us. Okay, so let's get right to the heart of the puzzle. Carbon has 4 electrons in its outer shell. You can think of them like 4 hands, ready to grab onto other atoms. But how in the world does it use just these 4 connections to build such a mind-boggling variety of shapes? What's the secret sauce? All right, let's start simple. Think of it like a basic chain of paper clips. At its most fundamental, carbon can just link its atoms one after another in a straight, continuous line. A perfect example is pentane, which you're looking at right here. It's just 5 carbons in a row, forming the backbone of things like gasoline. Simple enough, right? But carbon is way more creative than that. It can also form a main chain and then stick smaller groups off the side, kind of like branches on a tree. Check out this molecule, 2-methylbutane. You can see it has a main chain of 4 carbons, but then there's this one little carbon branching off. And for its next trick, the carbon chain can bite its own tail. Yup, the atoms can connect end to end and form a ring, creating what we call cyclic molecules. Cyclopentane is a great example. 5 carbons making this neat little loop. And this ring shape is absolutely critical in so many biological molecules. Okay, so let's dive into the first level of our architectural build. We're going to start with the most fundamental connection carbon can possibly make, the single bond. So when a carbon atom uses all 4 of its hands to form 4 separate single bonds, it creates this incredibly strong and stable structure. Each one of these connections is a direct link called a sigma bond. Think of it like a super strong rivet holding the whole thing together. And this super stable arrangement has a name, sp3 hybridization. Now, here's a cool way to picture this. Imagine you're trying to hold 4 balloons together by their knots. What happens? They naturally push away from each other to get as much space as possible, right? It's the exact same thing with these chemical bonds. They're all negatively charged, so they repel each other, pushing apart into this very specific perfect angle of 109.5 degrees. And the result of all that pushing and shoving is this. That 109.5-degree angle forces the molecule into this beautiful 3-dimensional shape called a tetrahedron. Our first hero molecule, ethane, is a perfect example of this classic, super stable structure. It is the foundation for countless other molecules. So that was single bonds. But what happens when carbon gets a bit more ambitious and decides to form a double bond between 2 atoms? Things get flatter. This setup is called sp2 hybridization. The carbon still forms 3 of those really strong direct sigma bonds, our rivets, but it also creates a new second kind of connection between 2 of the carbons. It's called a pi bond. You can imagine the sigma bond as a direct handshake, and the pi bond is like a second, gentler connection happening above and below that handshake. Now, because that whole double bond, the handshake and the high five, acts like a single unit, each carbon now only has 3 groups of electrons pushing each other apart. And with less crowding, they can spread out even further, creating this wider, more open angle of 120 degrees. And that 120-degree angle has a really dramatic effect on the shape. It forces all the atoms in the molecule to lie in a single, flat, 2-dimensional plane. We call this shape trigonal planar, and you can see it perfectly in our next hero molecule, ethene. This flatness is actually super important for molecules that need to stack on top of each other, like the rungs in our DNA. So let's just make sure we've got this because it's crucial. A sigma bond is that direct, super strong connection, the firm handshake. A pi bond is the weaker sideways connection that happens in addition to that handshake, with electron clouds overlapping above and below. That 2-part system is what makes a double bond a double bond. All right, let's take it to the final level of complexity in carbon's bag of tricks, the triple bond. This is called sp hybridization. Now, each carbon only forms 2 of those direct sigma bonds, but between the 2 carbons you get not 1, but 2 of those pi bonds. So you've got the one strong handshake right down the middle, and then 2 separate pi bonds surrounding it, one above and below, and another one in front and behind. So now, the carbon atom only really has 2 things to worry about, the atom on one side and the atom on the other. And to get as far away from each other as possible, what do? They just point in completely opposite directions. This forces the molecule to straighten out completely, creating a perfect 180-degree angle. And what you end up with is a molecule that's straight as an arrow, a perfect rod. This is the linear shape, and you can see it beautifully illustrated in our final hero molecule, ethine. You might know it as acetylene, the fuel that's used in welding torches.
Okay, so this is where it gets really cool. All these different building blocks, the 3D tetrahedron, the flat trigonal planar, and the straight linear shape, they can all be combined inside the very same molecule. It's like building a structure with a bunch of different kinds of Lego bricks.
Let's take a look at propene. It's a fantastic example of mixing and matching these shapes. See the two carbons on the left, the ones with the double bond? That whole part of the molecule is flat. It's trigonal planar. But then look at the carbon on the far right. It only has single bonds, so it snaps into that 3D tetrahedral shape we saw at the beginning. It's two shapes in one molecule.
And we see the exact same story with propyne. That section with the triple bond is perfectly straight, totally linear, but it's attached directly to a carbon with all single bonds, which has that familiar tetrahedral shape. It's a true hybrid of architectural styles, combining different geometries to get the job done.
So let's put it all together. This table right here, this is your master blueprint. It shows exactly how the type of bonding dictates everything else. For single bonds, you get that 3D tetrahedral shape. Throw in a double bond, it flattens out into a trigonal planar shape. And a triple bond, it straightens the molecule into a perfect line. This is the fundamental rulebook for how carbon builds everything. And this brings us to the biggest, most important point of all. We've seen how these simple bonding rules create very specific shapes. But here's the kicker. In our world, shape determines function, always. So the next time you think about DNA or a life-saving medicine, remember that their incredible power all comes from these simple, elegant architectural rules of carbon. It's a whole universe of function, and it all starts with these basic shapes.